Welcome everyone. Thank you for taking the time to join us for this webinar session. My name is Denis, and I will moderate today's webinar with the subject 5G, the revolution is here, deep dive into PCB fabrication challenges. First and foremost, I would like to introduce to you Kuldeep Johal, who is our speaker and subject expert. With more than 31 years of industry experience and deep knowledge on today's and future demands for PCB and IC substrate technology, Kuldeep is a true thought leader to our industry, and we are excited to have him here with us today. A couple of words about the webinar. The webinar will be divided into two parts, 40 minutes presentation and 15 minutes Q&A session. I encourage you to raise questions from the beginning of the Kuldeep's presentation and therefore to use the Q&A function, which you can find on the top right corner of your screen. Your questions will be visible only to me and Kuldeep, therefore do not hesitate to ask any related to the topic questions. I will try to cover as many questions as possible during the planned Q&A session at the end of the presentation. If the time allows, we will answer all the questions right away. Also, Kuldeep will be available after the webinar to reach out to you via email. Last but not least, if you face any technical issues, please make sure to enter the webinar via latest versions of Chrome or Firefox browsers. Now, let me hand over to Kuldeep. Please enjoy the session.
Thank you very much. First of all, I'd like to say a big thank you for all the attendees who are attending the webinar. I appreciate them taking time for their valuable time out of their day. And the goal of the webinar is to give you an overview of the key challenges that we will be experiencing when we move over to 5G. So having said that, the main outline of today's webinar is as follows. The main focus will be on the key challenges and the technology issues, but I'll have a quick introduction, a little bit of a discussion on millimeter wave, then the key challenges, and then conclusion and some questions. So if we take 5G, we see three significant trends that are driving the wireless industry to develop a fifth generation of network technology. I think the explosive increase in demand for wireless broadband services, which needs faster, higher capacity networks that can deliver video and other content-rich services. Another key area is going to be Internet of Things that is also fueling the need for massive connectivity of devices and the need for ultra reliable, ultra low latency connectivity over the internet protocol. Basically, it comes down to much higher content of video and mobile, web sharing, etc. And we need to sort of maximize this by looking at the available spectrum that we have today and for the future. As an example, just from a data point of view, Intel provided a sort of an interesting sort of scenario. Twitter, which has 270 million users, produces data at about 100 gigabits per day, and it's expected that when we move to autonomous vehicles, we'll be generating nearly 4,000 gigabit of data per day. So definitely 5G will drive new hardware that will enable many different types of devices, wearables, infrastructure, cloud and edge computing. So all of these factors are going to come into expanding the infrastructure from 5G. So what can we expect from 5G? Before I go into the expectations, I should really say, if we take 4G, the 4G revolution took approximately 10 years, and 5G is not going to be any different. And in this illustration, we have what 4G was, and the illustration comes from Quavo, I should say, and what we expect to see from 5G. So basically, what we expect to see is a much lower latency by tenfold. We expect data rates to obviously increase dramatically. And we also expect the available spectrum to be changed from the 3 gigahertz to the 30 gigahertz. And we expect connectivity density to dramatically increase to the 1 million connections in per square kilometer. So this is a very interesting diagram that I have taken from, the source was Yole, and it really shows the relationship of the timeline, as you can see there. It also shows you the speed and data rates as we move up across that way. And it is also showing the relationship of all of that connected to the frequency. And what we can see is that we have really three bands that are taking place. We have what we would call the sub uh, 1 gigahertz, which is traditionally going to be used for what we would say IoT and industrial applications. We then move on to the next band, which is the sub 6 gigahertz. And the sub 6 gigahertz is today, which is already being used. And if you look at 4G LTE in the US, this is many of the phones also are using sub 6 gigahertz. And some companies are also trying to trade this in as a sort of 5G situation, but it really isn't a true 5G. And then in this sort of area, we see smart cities, smart homes, and also smartphones, like I said. And then we come down to the final one, which is the millimeter wave. And the millimeter wave is anything greater than 24 gigahertz is really what I would say true millimeter wave. And we expect this to be for wireless, virtual reality, artificial intelligent applications, autonomous driving, etc. So when I look at technology, I think we have to, as a PCB industry, we understand that many different products are going to be manufactured to support the 5G. And you have to sort of dissect the type of product that you're building into the industry or the application that you are going to serve, because there's going to be a whole facet of different aspects that will come along with the type of product. So within these sectors, we can see that the electronics industry is already started the what I would call the revolution in terms of 5G growth, and we've already started to see such things as network switches, routers, servers, and this expected growth because of cloud and edge computing is expected to give an annual growth of 19%. And as we move on to the other types of technologies, we see wireless technology as near radio, small cell, customer premise equipment, etc., all coming along. We also see the smartphone, which is obviously a fairly complex situation in terms of the build structure that's going to be required in terms of the antennas and the RF filters, etc. And something that really may not be classified as 5G, but I look at it from a high frequency application, which is already being adapted by the industry, is the automotive industry in connection with LiDAR and radar, which isn't truly 5G, but we can see how these will be connected to over the internet to make autonomous vehicles, driving, etc., more level 5, as I would say. And then we finally have IoT, which is the next big billions of devices that will end up being connected into the industry. And I think one of the key things that we should take into account is the growth of what I would say cloud computing and edge computing. Since everything is about how fast can data be moved, and it's also how fast and how much of this data can be handled by these data centers, we will see that data centers will account for nearly 80% of 5G infrastructure spending. And this will come from the network transformation projects that are obviously going to be supported by the key providers such as Vodafone, Vodafone, and AT&T, etc. And key players are going to be in this sector are going to be Cisco, Dell, HP, IBM, Lenovo. And then we have the data component suppliers. And again, these are the guys that are driving the CPUs, GPUs, etc., and also the communication application processors, etc. Intel, Qualcomm, Broadcom, Avago, AMD, Samsung, NVIDIA, to name a few. And then finally, what we would say is network transformation providers. These help telecommunications and other communication companies to upgrade their networks. And these are going to be companies like Ericsson, Intel, Nokia, Samsung, Huawei. And these will all fuel the PCB industry that's going to be coming along. The next slide, which I'm going to talk about, is really the millimeter wave. The illustration at the top really shows you what sort of spectrum we are talking about. As discussed earlier, we can split this into two main sections from a communications point of view. The sub-6 gigahertz and then into the true millimeter wave. Another key factor that you will observe is that when we talk about spectrums, each of the countries will have their own individual spectrums that are authorized from a government perspective point of view of the allocated bandwidth that the commercial use for 5G will be placed. And what we can say is that typically that bandwidth is going to be anywhere from what I would say 24 gigahertz all the way up to sort of coming up to about 30 gigahertz. And that's going to be the main frequency where 5G is going to be used. So as we move to 5G, we're also going to see the use of massive MIMO and beamforming to ensure that we can get line of sight to make millimeter wave, given that millimeter wave propagation distance is much shorter than obviously the other spectrum radio waves that we would typically use. Another key factor I think everyone has to understand, like I mentioned before, millimeter wave in 5G is not going to be a standalone system. We're going to have several areas, just like we still have 3G, we have 4G, we will have 5G and a combination of 4G and 5G. So we'll have a multitude of what I would call spectrums being used, and the NSA is a non-standalone system, and then you'll have your true standalone systems that will operate in the future. So now we come to the main section of the webinar, and I'm using this fishbone to illustrate some of the key challenges moving to 5G PCBs. Many could say this is not new and that we've been producing millimeter wave circuits for many years for military aerospace applications. I think the challenges are now that the volumes of products that we'll have to build, the material sets that we have to use, the cost and the functionality. If you really think about the processes that are being used in commercial versus military and aerospace and the current let's say connectivity densities that are typically used in the other industry are very different. And I think the requirements are also very different. So if I take this and break it down into the four main categories, the first one is signal integrity. This essentially ensures that the signal that is moved from point A to point B is transmitted in sufficient quality and integrity to allow effective communication. The next challenge is inductance and capacitance. And basically, this impacts are normally designed into the circuits, and these tolerances are calculated by the OEM designers. Basically, when a transmission line is used to connect a circuit, the goal of the circuit is virtually to be transparent or invisible. This means that the physical and electrical connections in the circuit components do not affect the circuit operation. Another challenge that we're going to talk about, which is really hot, as you could say, is the thermal management. As PCB and components are heated, we know that the properties change when they get heated. We also know that thermal conductivity, electrical properties affect each other, and these effects can lead to performance issues. And as 5G continues, we see the demand for higher power and increased functionality and increased I/O density is definitely going to mean that we have to have higher power. That means there's going to be higher thermal issues in the future. A final section that I'm going to talk about is EMI shielding. At the end of the day, EMI shielding is in order to ensure a reliable performance. The number of IC packages on a 5G will require shielding against electromagnetic interferences, especially in the case of the mobile devices. And solutions are becoming more challenging as we increase the I/O density and reduce the PCB area. So if I focus on signal integrity, as I mentioned, signal integrity is one of those hot topics, not only for the smartphone industry, but pretty much for many of high frequency, high speed circuits. And it's really been a hot topic over the last, say, 2 years or so. As we shift to these higher frequencies, the signal integrity poses many challenges for the PCB. So signal losses are impacted by how that signal is moving. We already talked about that. And a few milliseconds can really change and have a cascading effect in terms of the signal chain losses. So the challenges are magnified as we continue to shrink form factor, as I mentioned before. And one of the key things in signal integrity is going to be the physical parameters of the line. So in terms of the trace length and the actual shape and the surface roughness. So physical shape and roughness, and that goes to all sides, including the bottom. So a lot of the PCB designers and OEMs are obviously looking at decay, dielectric decay and DF of the material selection, conductor roughness, conductivity, skin effect, solder mass thickness, and moisture factors are all playing a role. So when I break down the signal integrity and its key factors, and you can see by the pie chart here that one of the key factors is what I mentioned before is basically the length of the conductor plays a key role, the material properties, and another factor is going to be the track conductivity and dielectric thickness, and all of these are playing a key role, and track roughness. So a combination of all these factors will obviously have an influence at the end of the day. And one of the key things that we can see is that the industry itself is starting to use these, what I call low loss, ultra low loss materials. But one of the challenges that we've seen with ultra low loss is the cost factor. And then customers are trying to build, or OEMs are building the products, telling the customers to build with a mixture of dielectrics. So you will have a low loss dielectric on the top, and you will have standard FR4 materials in the center. And what this poses is challenges for the PCB supplier in terms of your desmear process. Now you have to have hole roughening that is going to be sufficient to get good adhesion of the electroless copper without any blistering and good coverage, and ensuring that you are roughening both the ultra low loss materials and the standard materials. So again, it poses more challenges. And again, I think Aditech has been working with fabricators in optimization for the chemistry in that side. Another factor that we have seen is sometimes we see leach out of some of the materials affecting the surface finish. But again, this is depending on the finish and depending on the dielectric materials that we see. As I mentioned before, one of the key factors that we have been working on, especially for servers, switches, routers, where signal speeds are moving up and up, and data gigabits is changing as well, as we see that. As we move to these higher frequency, we see increasing results of increasing signal loss. These losses are really affected by the skin effect of the conductor. And if you look at the table here, this table illustrates the impact of trace roughness. So you have a smooth trace, then you have a rough trace, and then you have the effect of skin. And this is all related to basically the frequency. So as the illustrations show you at the below, you can see how trace roughness is traditionally being used to really get good adhesion of the trace to the dielectric. And this now shows you what we have to do, in other words, to move to this. And the relationship is showing how the signal is moving from a low frequency to a high frequency. So this is a key area. And what we can really say is if we improve our surface roughness, we can improve signal integrity. And typically that signal integrity can be 7 or let's say 5 to 8%. But talking to signal integrity engineers, that's still a gain that they want to see. So in this slide, what I show you is a table of all the key products that Aditech has been working with. And you can see there's a whole blend of different types of chemistries being used, and the number of steps are also different. But I think I want to point out to a couple of things that are really key. Number one is obviously the edge depth. And edge depth is a functionality of getting to that smoother trace. Another key factor is that in some applications, you can get away without basically just making a modification to the chemistry, but using your standard equipment. And this falls into products like this, the bond film HF and the bond film MS range. But again, what we're doing here, and this is the key, is we are gradually dropping the etch rate, and it's being used in a standard process, which is key. At the same time, when I mentioned a smoother trace, we still have to meet all the requirements that the PCB companies are putting in terms of the reliability and performance. So here comes really the challenge of making this technology work with ultimately a smooth surface topography. In this slide, this is really talking about the impact of signal integrity and the relationship to surface finishes. I've got a lot going on in this slide, and I'm going to start off with really one of the key factors that we know is length, width, and height is affected, roughness is affected, dielectric is affected. But another thing that we should pay close attention to is the type of circuit that is being used. We can see two types of circuits here. You have a microstrip line there, and then you have a grounded coplanar circuitry. And you've got your transmission lines between signal and ground. And you can clearly see that based on your thickness of your dielectric, you will have some potential interference between your signal trace and your ground trace. Added issue that you can see is if you move to a ground planar waveguide, you will see that there's potential risk of signal interference between adjacent traces as well. So that plays into this whole aspect. On the right-hand side, upper right-hand side, you can see that I'm comparing now what happens as we move the signal faster through the trace. You can see that at 1 gigahertz, the signal is moving through the solid copper trace. And as we move to the 20 gigahertz, we suddenly see that the signal is now moving to the edges and the bottom. So clearly, this is going to have an influence on the surface finish and the treatments that are being used. So we've already mentioned about skin effect and how the skin effect is being changed. Another key factor that we should talk about is really the impact of conductivity. Now we can say that, let's say a traditional finish like ENIG is being used there. And one of the challenges with electroless nickel and high frequency applications is that the conductivity is not good. Plus, as the skin effect is increased, or let's say reduced, We can see more of the signal now being transferred through the nickel instead of the copper, which again is having a magnitude effect on it. And finally, you have another factor, which is the foot. And especially, as I explained in grounded coplanar waveguides, this foot then has an influence on the top and bottom of the ground, as well as adjacent traces. So you can clearly see that there's going to be some influences on nickel gold. So when we move to what finish could be good, and I should say one thing on my previous slide that I didn't mention, was that if you looked at conductivity, there's copper and then there's silver. And so everyone should say, okay, why don't we just move to silver? Okay. And in this case, what we did is we did some comparison tests in terms of data that compared standard um, electroless palladium autocatalytic gold with silver and INIPIG. And what we could see is the results that came out of this, that the signal losses on EPAC was just as good as silver. And so we could see that this is a potential finish that could be used for high-speed applications. But at the same time, a finish isn't just about signal integrity. You have to really choose the finish based on, is it going to be used for multiple solderable applications? Is it going to be used for conductive adhesives? Is it capable of doing fine lines in space? Is it for flex, etc.? So there's a whole gamut of things that will need to come into when it comes to your process selection. So, and these are some of the key things that I think everyone needs to understand in regards to that. So moving on, another type of finish, and we have some signal integrity data and the comparisons of thin tin and thick tin. And it's compared against a copper trace, and this data was connected with Rogers. And what we could see is that obviously the thickness of tin has an influence. Just again, we talked about that in terms of the relationship. But we also see that tin does have a difference in signal integrity in comparison with the range of materials in this area. However, what I can say is that regardless of that, you also have to consider the tin. And if you take a circuit that is open to the corrosive atmosphere, whether it be tin or silver, you have to think about byproducts and corrosion products that are affecting conductivity. So just like tin will not stay the same, and silver will not stay the same. So once the silver is no longer a pure silver, you will alter the conductivity, which is then going to alter the performance of the finish. So definitely one of the key things to look at is how is the circuit going to be used and what kind of environment it's going to be used, and then you can really make a decision. One thing I can say about high frequency applications, immersion tin has already a good proven track record for the automotive industry, where it's been used for LiDAR and radar PCBs. And typically the operating frequency for these type of applications is 77 gigahertz, and they're gradually moving up to 80 gigahertz. But also you have to think of the humidity, high temperature of some of the circuits that are operating in that environment. And so it can stand to those type of harsh environments. So I think circuits for antennas and the application of the surface finish for antennas is going to be really interesting, how that develops and what kind of surface finishes they will move to. So we now move on to the next key area of discussion. This is very important in RF and microwave circuits, as we can see. And as frequency increases, the energy is lost in the transmission line, which is more difficult and more costly to recover. And there are basically 4 parameters that we need to consider when we look at impedance and capacitance control. One of those is inductance, resistance, capacitance, and conductance. And when you combine this with the dielectric constant of the insulating material, this is how you can sort of calculate your impedance transmission impacts. So efficient transfer of energy is one with minimum amount of reflective loss due to inductance mismatch, as well as the amount of resistive loss due to mechanisms such as skin effect. So inductance should be kept as low for efficient operation, and this is associated mainly with the design. The second parameter, capacitance, which is determined largely by the circuit designers, and the second factor, it's also impacted by the manufacturer's capability. And one of the things that I remember speaking to an OEMs is that they set the certain parameters that the OEMs expect the circuit to do. And if we have deviations in trace dimensions, spacing, dielectric thickness, this will impact the performance. So its key importance is to control manufacturing methods so that the end results are the desired results. So what does this mean? Basically, what it means is that from an OEM perspective, what the OEMs see is that from circuit to circuit, supplier to supplier, they are seeing variations. And when you see these variations, it's very difficult to incorporate their designs in a way that the circuit is accounted for. So I see that the printed circuit board industry for 5G will be transitioning into more of a statistical process control and doing a lot more analytics on the outputs of the manufacturing process, and dialing down the variabilities of the process is going to be one of the key factors that I see moving on. As an example, I'm showing here, one of the things I mentioned was capacitance and inductance. And inductance and capacitance is really also affected with the trace length. So all of the designers are trying to decrease trace length, and this is one of the key factors that they can help to reduce the impact. And I'm showing you here an example of a via in pad, and if you look at the trace difference, the length is going to be greater. Sorry, I meant to say this one. Dog bone effect is where the trace is longer, and a via in pad, your trace distance is shorter. So what does this mean? If you took this and you would then said, okay, I've got a via in pad, that could save you approximately 200 to 300 nanometers. And if you say, okay, sorry, microns, and if you take, there's 1,000 IOs, that could be up to about 250 per each via in pad, coming down to a 25 centimeter saving. So again, this is another way circuit designs will change in the future for 5G. This next slide really, as I mentioned before, there are many factors on inductance and capacitance, such as the thickness between the alternating copper and dielectric layers, such as the lamination, solder mass thickness, and trace height. As you can see, that another key factor that brings in this variation is the CTE differences between the prepreg and the plated copper. And what we see then is what's key here is the dielectric differences between here to here are going to then influence the overall performance of the circuit. This means that from a PCB point of view, materials are going to be key, as I've already mentioned, but the plating processes also are going to be key. And we have to focus on, do we need to spend more money on capital investments to improve our plating? Do we need to reduce our current density in plating? Do we need to use reverse pulse plating? Or do we need to use the next generation additives to incorporate the benefits of more uniformity across a large panel? So all these key factors are going to come into where we want consistency. Another factor on impedance control, which is a very important factor, is what I would say is the trace dimensional control consistency, which is the line width and height and space are critical for signal integrity. And you could say, well, this is mainly driven by key parameters such as lithography And you could say it depends on my differential etching approach. So that's true. And if we compare and we take, say, a print and etch type of circuit product, we will see that we will end up with a trapezoid type of pattern. And this basically then changes the area of the top, the bottom, the sides, etc. And so you can see a graph here. This is courtesy of AT&S that had done some studies in terms of how the surface topography of a trace is influenced by the different frequency. And you can see the signal delay is reduced if you have a much squarer trace. So what does this mean? This also means that in 5G, as we increase I/O density, there's a potential that we have to move from print and etch approaches to more of a MSAP approach, where we will have the ability to create finer traces, but also much squarer traces. Just like the industry in IC substrates has already transitioned to SAP, again, this is going to be done through different dielectric materials, and we also have to think of cost and functionality of how these processes have to be changed within that. So basically, what we can see is that another illustration is shown here, where if you run something at 28 gigahertz as an example, what we're seeing is fabricators are then being pushed to have less than 5% inductance tolerance variations. So this is going to be, again, another challenge. This means that we have to be 60% better than where we are today. Thermal management, which is obviously very interesting. I remember seeing an article back in July 2019 when a reporter from Wall Street Journal tested one of the first 5G millimeter wave smartphones. I think it was from LG. And I believe it was in Atlanta where they tested a 5G network. And what was interesting, he found that the smartphone was super fast, worked fantastic for about 40 minutes of operation. And then all of a sudden, the smartphone had to keep on reverting back to 4G LTE. And then afterwards, what the engineers found out was the reason the shift was resulting was because the processors was overheating due to the amount of data that was being processed. So the software forced the system not to overmelt, but to move back to the lower frequency and continue operating. So I think this is not only for smartphones. We will see this thermal challenge especially occurring on 5G cell towers, where the implementation of massive MIMO and beamforming will create. And so this is going to be a very challenging topic, and functionality is obviously dependent on controlling the heat in and heat out. And so in the fishbone, I've given you a few sort of areas that we see where the PCB industry is moving towards a via farm, through hole, current density is a key factor on it, and coin is another chance of reducing heat. So in this slide, I show you and mention again the key factors that are influencing this, and so I don't need to repeat that. But one of the ways that the PCB companies have been looking at this is if we look at, say, thicker copper plating, heavier copper, and so instead of just plating the 25 microns, but even go in at a thicker 30 microns, etc. But again, with some of the PCBs, you've got to look at through hole and the aspect ratios and the performance of the throwing power to be equal to 100% or better. Another approach that we can see that the industry has been used, and I think this is traditionally being used by a lot of the military and aerospace types of industries, where they have aluminum or copper metal backing to transfer the heat from the PCB. I think one of the challenges with that is the impact on the Z direction of that. So another key area that we've been focusing on is through-hole filling, and this would support high current density at the same time would not impact the Z direction. And so moving on. This slide here is going to talk about some of the work that was done, and some of it is you can even find out on empirical data where you have a source that is creating the heat, and then you have the victim, which is the PCB and the functionality of the product. One really also important aspect to note is that as signals are generating heat and as they're moving faster, we will see the heat is focused and concentrated in the high current density areas of the trace. This is multiplying the amount of current that is subjective to those particular areas of the trace, which is then making the thermal heat dissipation much worse because now you've reduced the trace area considerably if you compare it against where the thermal heat mass would be moving through the whole trace. So going back to through-hole filling, what we can say is that if you take a traditional conformal fill, we'll see that the total thermal resistance is about 122 Kelvin per watt. And if we do via impad and we use a conductive epoxy type of material, we can drop this, but it doesn't drop dramatically down to about 116 Kelvin per watt. And as we move to a completely filled through hole, this dramatically changes the thermal resistance. Atotech has been working on this and developed a horizontal system, which is a two-step system, which requires a sort of a bridge step first, and then followed by the filling step, which is basically filling two blind microvias on the same time, and this is achieving this through-hole filling. I should also mention on the previous slide that one of the challenges is obviously aspect ratios and how far can we plate. And I think, the challenges are being pushed from 4:1, 6:1 and greater is the key areas. Moving on to EMI shielding, what I can say, sorry, I should go back. Moving to EMI shielding. EMI shielding is becoming very challenging as we increase the number of components and the component density is also massively increasing. We're also at the same time shrinking the PCB. And as we move to faster speeds, they generally require higher currents to produce them, which can then lead to unintended radiated emissions. These radiated emissions increase the crosstalk and cause potentially a digital device failure. So one of the key purposes of EMI shielding is to minimize the EMI effect on RF circuits. And so we can do this by multiple paths. And a traditional path has been metal screens or metal cages. And I think the overall industry is trying to find better solutions because of the metal caps in terms that they do also create other side effects as well. So if I go to the next slide, we can see that I've sliced a cell phone, and it's amazing in the cell phone is where shielding is critical, but we have many, many areas that shielding is required in terms of the front camera, the rear camera, the battery side, the home key, the mini PCB, main PCB, the Wi-Fi side, and the rear camera. So we require a lot of shielding applications there. One of the approaches I've just mentioned to you was the traditional approach was these metal can approach. We see the industry moving to more of a spray conductive paint type of application. And you can see that there are pluses and minuses in both cases. And we also see the sputtering. What Atotech has been doing is trying to develop metal stacks that are plated. And one of the key things is that we can, when you plate a stack, you can alter the thicknesses considerably thicker than you can effectively and economically do with what I would say sputtering or a spray type of paint. And in the next slide, we will discuss a little bit about some of the stacks that we have discussed. So the table here shows you some of the, let's say, flavors of the metal stacks that Aditech has been testing. And we've done a lot of this testing with some key OEMs. And what we've done is there's two challenges that we had to obviously tackle. One key challenge was developing a process to metallize the outer mold compound. And that was where we needed to meet the OEM requirements from an adhesion point of view. And the second was we developed a nickel iron solution that was consistent, giving an 80-20 alloy, so 80% nickel, 20% iron. And this had to be done in a wide operating range, because as soon as you vary the nickel iron content, you're going to vary your performance in terms of EMI shielding. And we did some testing with, as I mentioned, with the OEMs. And the testing was done with really what I would classify as higher frequencies and lower frequency applications. At the lower frequency, the skin depth is larger and the conductance is increased and the current absorption is increased, which results in an increase in magnetic flux. Therefore, the metal and high permeability of nickel iron can be implemented to help and redirect the increased magnetic flux. Another approach was the higher frequency applications where skin depth is reduced, effectively decreasing the conductor cross-sectional area, and the conductance decrease and current absorption is reduced. Therefore, higher conductivity such as metals such as copper is needed to counteract the skin effect and sustain the shielding through absorption capability, reducing the current, and in turn lowering the generated magnetic flux. So what we can see is that by using different metal stacks, we can find a path forward. However, I would say this is not a commercial, fully fledged technology that is moving out there. We can see that this technology is being tested, and let's see if it gets adopted by the industry. And just on a point to note, from a PCB point of view, what could you do? From a PCB point of view, we can see some components potentially being embedded into the PCB, and this could also reduce the interference between other components. So we see that as a potential growing aspect of it. So as I summarize here, that we can see that all these factors are going to come along for the printed circuit board industry. There are challenges: faster data rates, wider frequency, thermal management, signal integrity, EMI shielding, increase of antenna in package, system in package, increasing power, asymmetric builds, and the coupling between traces. And what I can say is the industry is faced with all these challenges, but at the same time, I think these are opportunities for the PCB industry to have good opportunities in key areas of the next revolution of growth. And what I'm pointing to this slide is that if I break down some of these main categories, Aditech has been working in impedance control by moving to finer lines of space in terms of the methodologies of plating and the additives used and the uniformity. We've been working hard in terms of signal integrity, in terms of the surface finish, as well as the surface topography and roughness of the traces. Thermal management, we explained just now, in terms of through-hole filling and EMI shielding. So this sort of provides you a sort of overview of where the problems are and the solutions. And I appreciate and thank you for you listening to me. So we'll open the session up for Q&A.
Thank you, Kaldeep. It's time to proceed with our Q&A session. I would like to remind you that we will cover as many questions as possible during our Q&A session, and all the rest will be answered by Kaldeep after the webinar via email. So let's start with the first question. Traditionally, adhesion was supported by roughening the copper's surface. Was a non-roughening adhesion promoter? if the surface is now smooth, how to achieve bonding of the dielectric to copper?
Yes, I think that is the ultimate challenge question. And we have extensively been working in this area because let's say your traditional adhesion promoters have always relied on a mechanical bond. Like I explained in the photograph, you have this very rough topography. And what we need to do is to go to that smoother topography. And so you can do that in a sort of systematically by reducing the edge depth. But at the same time, what you've got to look at is that's not going to be good enough. So when you go to ultrally smooth traces, we have to rely on a different approach. And the team that's developing these products have really been looking at how can we change from a mechanical bond to a chemical bond. And ultimately, that has to happen. Now, the challenge with chemical bonds is that you can have a functional group that works great with one type of resin. So the challenge becomes to have a functional group that can work with multiple resins. And so to make that happen, what Atotech did different was they actually started to develop our own chemical molecules that have the selectivity and connectivity from the resin to the copper so that we could really optimize our formulations to give you that what we call ultra neap non-etching adhesion promoter.
Thank you, Kuldeep. So the next question from the audience is when silver is such a good conductor, why not just using immersion silver as surface finish for high frequency applications?
I think I mentioned this before, that silver from a conductivity, as mentioned earlier, was very good as a conductive material, but it doesn't stay conductive if it's exposed to the atmosphere. And I mentioned that, one of the key things is sulfur in the atmosphere. And sulfur in the atmosphere certainly leads to corrosion products, regardless of which surface finish, ENIC or whatever. But at the end of the day, these finishes, which are based on what I would call precious metals, are generally going to be better than silver. So the concern I have with silver, and it's not a dig at silver, but is how can silver maintain its conductivity in a sort of corrosive atmosphere? The second point that I didn't touch on, but once you have a soldered joint, you have a silver copper intermetallic, and then you have a tin copper intermetallic, which is traditional. And we can then see if you compare the conductivity of copper tin versus copper silver, you will also see some variations that copper tin intermetallic is a better conductive material. So hopefully I've answered that question for the audience.
Thank you. So up to what temperature range is palladium an effective copper diffusion barrier?
We've done some testing in this case, and this was done for an automotive application. And we have found that a 50 nanometer thick palladium layer was tested to 500 hours at 200 degrees C. And we confirmed that it still maintained its diffusion barrier characteristics by Auger. So it does have a fairly long thermal budget from that perspective.
Okay, thank you. So the next question is, wouldn't immersion silver be better conductor compared to palladium gold?
I think, like I've mentioned this, I think this question we've really pretty much answered. So I'll just go back at the end of the day. I think what we have with palladium gold is that you have the precious metal influencing the performance of, let's say, preventing oxidation of the system. And I've already mentioned in the other aspect is that you don't have any concerns with silver in a point of view of dendritic growth as a risk, and you have the potential of shorts. But at the same time, so these factors will not influence the palladium gold. So there are a few other advantages in that aspect.
Okay, thank you. So the next question is, vertical stresses caused by thermal expansion in thick boards is more severe as on thin PCBs. Will this have an impact on mutavia reliability too?
Well, I think microvia reliability is a very hot topic and a very interesting topic because as the industry is moving to more and more stacked blind microvias, we can see that the industry typically has gone to pushing the envelope from one to three stacked blind microvia. And some of these are staggered and some of these are not staggered. And we've done a lot of work in this, and we can say that you could argue that the mobile industry, who is making substrate like PCBs, can already make 10 layers stacked blind microvias, and their performance is great. And that is absolutely true. However, on a printed circuit board, we do use different dielectric materials, and we see that as you shrink the pad area, and as you look at the interfaces, one of the key areas that we focused on is the copper to copper interface and what is influencing that integrity. So this is a very short way of answering that question. Yes, we certainly have very deep understanding of what makes it happen and what makes a good joint and what prevents a good joint, and we know how to look at a product and say this has a bad joint or a good joint. And there is a separate webinar on this topic coming up in the future.
Okay, thank you. Forward to the next question. At what speed can you plate copper when it comes to heavy copper thickness?
Well, from Atotech's perspective, we can go up to 25 ASD. That's approximately 5 microns per minute in a DC mode. But this can be run with pulse plating as well, and it can be in both a vertical, a VCP with soluble anodes. That's what I would say.
Thank you. The next question is, what is the maximum aspect ratio for a through-hole filling?
I think if we take traditionally the circuit boards, let's say a 1.2 millimeter type of PCB, 1.6 millimeter, etc., and the size of the hole, etc., and we look at the aspect ratios, what we find is two challenges. One is absolutely the maximum aspect ratio that we can fill. As I mentioned before, this is targeting towards 4 and 6 to 1 aspect ratios. Are we there 100% there yet? No. But one of the key challenges of filling a large volume of hole is the overburden. And then you have to remove that overburden by etching. So, as I mentioned before, by using a horizontal tool with reverse pulse, we can minimize the amount of surface copper on the surface, which is then going to allow us to fill deeper and higher aspect ratios. And I think one key question to answer the question is a very difficult question because it also depends on the number of holes, the current density, and how the holes are distributed across the panel. So you will have isolated holes and you will have a whole area of high number of holes. And if you think about it, the isolated hole will obviously plate thicker copper, and the high density number of holes will plate thinner. And so there are tricks to try to help. And one of the areas that we're working on at the moment is how can we take the net effect of the circuit design and have a neutral effect. And I don't have enough time to go into that, but that is a key area. So from aspect ratio, absolutely go down to 3 to 1 is possible. Moving to 4 to 1 and 5 to 1 is a function of the overburden and what we can do about that. But this is where the industry is pushing everybody, not just Atotech, is that they want us to drive this. And I think this can happen. It's just going to take a little bit more development work to make that happen.
Okay, thank you. And the last question of today's session is, can through-hole filling be done in vertical mode?
Yes, it can, but unfortunately, there are limitations to the panel thickness that you can handle. So that's one of the key factors that you could think. But even for thicker panels, the key challenge with vertical mode would be the inclusion of voids, okay? Because if you don't have the reverse pulse approach, and which is combined with the redox solution, which is basically not only reverse, but you're also etching the solution on the surface because of the ion redox reaction. I think vertical is a solution, but as you push the current density, as you push the aspect ratio, you're going to be challenged a lot more in the vertical mode. And you also have to think about your investments that you have in the vertical mode in terms of impingement, solution movement, anode to cathode distances. So there's a whole bunch of key aspects that can improve the situation, but ultimately I don't believe that you can get the same kind of result in a horizontal mode which you can with the system that we would propose. And I suppose at the end of the day, the proof of the pudding is the demonstration of the performance.
Okay, thank you, Kuldeep. So it's time to wrap up our webinar session. Thank you, everyone. We really appreciate you being here. Soon you will receive the replay link for this webinar. If you like this session, feel free to share the link of the recording, which will be available to view after the receiver registers. Our next webinar, The Importance of Reliability when Plating Electrolytic Stacked BMVs, will be held on Tuesday, 30th of June in 2 sessions to address different time zones, 9 a.m. CEST and 8 p.m. CEST. For our upcoming webinars, please visit autotech.com/media/webinars. We will also keep you updated about our webinar schedules. Stay healthy, safe, and see you next time. Thank you.